So now we have the next talk here. We have Ashwanth Kumar and Sriram Ramachandrasekaran from Index, and they're talking about why they built a distributed system at Index. Please welcome them.
Thank you, guys. Good afternoon. First of all, thank you to Sriram for the wonderful talk in the morning. I really liked the stuff that was covered in the morning, so thank you. And I personally learned a couple of things along the way. Okay, so able to see the slides here. Yeah, thanks. Okay, so I have Ashwanth with me. He's also from Index. We are going to cover some material around why we kind of built a distributed system from scratch using existing libraries, but not systems. And I'll also cover some of the motivation behind it, what was the problem we had, and what are the trade-offs that we had to take for us to actually take this call. I will walk you through some of the meta stuff, and Ashwanth will walk you through the actual implementation, just so that we're kind of clear. So let's kind of get rolling. Yeah, so I've been at Index for the past 5 years, mostly worked on all the data pipelines, worked on ML-related problems, worked on a couple of distributed systems, worked on data ingestion, so pretty much most of the stuff that, that we have done at Index. Just setting some context of the problem space, what we do is we kind of strive to be world's largest product database. So we collect product information from e-commerce stores, and then we kind of ingest them and store them into our internal data store, from which we run a lot of algorithms on top of it to kind of structure the data. So essentially what we are dealing with is HTML content about products that you deal with on a day-to-day basis. It could be the backpacks that you're carrying, the spectacles, or the laptops that you have, stuff that is being sold online. So that's the domain. Now let's just get a little bit more on the details, right? So we deal with 1 billion+ products. We have products across close to 6,000 categories. We are dealing with close to 70,000 brands, and we are kind of having to deal with close to 2,000 different e-commerce stores, right? So that's at a high level what we do, and once we kind of start collecting our data, right, our data pipeline looks something like this. So we kind of crawl data, and then once you crawl the data, you get HTML. On top of the HTML, you need to kind of run some either heuristics or algorithms, which we call as parsers, which kind of tell us whether which portion of the HTML is the title, which is the price, which is the image URL, which is the specification, and stuff like that, right? And this changes, as you might know, this changes for every e-commerce store that you deal with. Every store puts information in a different way, so the challenges are, huge. So we kind of parse this content, and then post that we kind of have this stage where we have to identify duplicates within the same store. So we call this a dedupe problem. Post that we have a classification of products, which kind of, we take this 1 billion+ corpus of products and then slot them into 6,000 of these buckets. And post that we kind of try to enrich the product information with more and more metadata or more and more attributes of the product, trying to describe it better, like the color of the product, the size. If you're dealing with a mobile phone, what is the RAM capacity? What is the storage capacity? What is the OS that it's operating on? Do you have connectivity or not? Stuff like that, right? And post doing all of this at a product level, we kind of deal with a bigger problem, which is in the academics, it's called the entity conflation. We call it as product matching, essentially trying to identify the same product across different sources, right? This problem has been prevalent ever since we have kind of dealt with information or data. Disparate sources of data in huge enterprises, you have information spread out everywhere. It's the same thing, it's just that the enterprises are different. We are trying to consolidate that. So once you have kind of identified products that are the same across stores, one of the things that you want to do is kind of take this information and surface it out so that people can do interesting things on top. Some of the common stuff that we have people do, are, just one second. Yeah, while this is getting sorted out. So some of this common stuff that I see people doing are doing pricing intelligence on top of it. They're doing inventory comparison on top of the stuff, the data that we house and all that. So essentially it is for retailers and brand and category managers to understand how to use this information and kind of take decisions for the day-to-day work. Right? So in this entire pipeline, there are a few critical pieces which need its own persistent store. We have the HTML content that we crawl. We cannot afford to lose it, because if we want to improve algorithms, we can go back to this HTML content instead of crawling it from the web again. So it's important for us to store this content and then be able to run some processing on top of it. So HTML store, which is the crawl store, needs a specific store. And then identification of duplicates within the store, that also needs a specific store. And the final API that we house and send for the outside world, that also needs a database or a store, right? Of course, there are other pieces which are kind of need stores and all that in between, but I've kind of hidden them away. Now with this context, right, I kind of brought in store specifically because there are two problems that we need to deal with. One is the compute, the other is the state. Dealing with compute and state at a high scale means problems. You're asking for trouble. So one of the things that we actually tried our first solution with HBase, and then we tried something with HDFS, and then we tried something with S3. We had a bunch of issues with each of these things, and then we kind of wanted to take 2 steps back and look at what are the problems that we have, what are requirements, what is on offer from the industry in terms of open source software systems, or what are those might be, and then try to understand and match our requirements with what is there, right? So I'm going to walk you through now the properties that we want from our system, and then what we get, what is available, and what is the trade-off, right? So the bottom line is that we want to handle scale, terabytes of data. That's a given. At any point of time, we should be able to handle terabytes of data. We should be able to do functions, run functions on top of it. Something like it could be as simple as aggregating some information about stores or products and something like that. It could be as simple as that to running more complex predictive algorithms on top of this data, right? So I should be able to run algorithms on top of this data. I want these systems to be fault tolerant because there are dependent systems, there are customers who use this data, so we don't want failures because of the fact that our systems are not able to respond, right? And the most important one, I would say, is operability. We want to ensure that these systems are operable, and it doesn't become a black box where we find it very, very hard to understand what is happening, nor it becomes too difficult that you just need 1 or 2% to handle the entire thing, right? So we wanted to make it more approachable and operable. So these are the properties. And problems of this scale, traditionally, if you look at it, it's been solved in a very tiered approach. You kind of segregate your logic into tiers, and then you kind of see how to scale your tiers independently, and until your database becomes a bottleneck, right? And once your database becomes the bottleneck, then you're kind of running behind to see if you want to scale vertically, or do you want to re-architect it? Do you want to pull the SQL from here to the Java layer or the Scala layer, or whatever you want to do, depending on the stack, right? Basically, you're going mad with this thing because you don't know how to scale this because the database is not in your control. So essentially what we are trying to do is we are trying to deal with scaling data systems. This is not scaling a database, this is scaling data systems. What that means is you have to handle data as well as computes on top of the data. The computes are domain-specific computes. Again, it's not irregular min and max. Cool. So the first thing that we thought is, okay, let's split the problem. Let's handle the data separately. Let's handle the compute separately. We have key value stores to help us with a lot of these things, and they are distributed, and they kind of advertise a lot of really, really powerful features and performance improvements or performance benefits, right? So we kind of evaluated a bunch of things, Bigtable, right from Bigtable, followed by Dynamo, Cassandra, Voldemort, and there's plenty of other stuff until Foundation DB last week, right? So we have these databases that keep coming up, solving different use cases and different needs and all that. That's primarily one approach that we try to take and see, okay, is this going to help us with solving some of these problems that we have, right? If you look at this, right, it really looks good. You have users using the system, you have the services that are talking to this distributed database or data store, and things are running fine as long as you start noticing something, that a particular node is starting to become like your hotspot, or a couple of nodes are becoming your hotspot because your data is not distributed properly. You didn't expect this kind of distribution of data, nor you expected this kind of distribution of your query, right? So you go back and see, okay, what should I do now? Should I rearrange the data? Should I reshuffle this data? Should I do something there, right? And invariably, if you end up building a distributed system or using a distributed system, you know that you are always talking over the wire. Talking over the wire is something that we don't really see as a very, very important thing that we need to understand, but it involves a lot of complications that go behind it. And one of the things that's, as a user, that I see is latency. The first thing that hits me is, I'm making a call, why does it take so long to come back, right? So the first thing that you kind of think about when you deal with systems over the wire is latency. And once your latency starts to focus on a couple of nodes or a couple of processes that are involved in the entire system, then you don't have any further way than to keep splitting the data further again and again. So this keeps going. You keep doing this a couple of times, and then you realize that there is something off. I mean, there are few nodes that are not utilized. There are few nodes that are utilized more. You're not able to strike a balance. You don't know what the solution is, right? So, I mean, we tried this approach a couple of times, and then we realized that this is not what we want. There is something else that we want, right? So we said, okay, let's kind of bring the data and the compute together. Let's try to co-locate the data and the compute so that I can kill the net latency. I don't want to hop over the wire to do my compute. I would locate my compute where the data resides, at least for the most part, right? So if you look at existing systems that are available, you can take HBase or anything else. They have this support for running compute along with the data, which is called coprocessors. It's inspired by Bigtable again. Bigtable has this thing called coproc. HBase is like a true implementation of it in some sense, except for the fact that Bigtable advises it as a separate process, whereas HBase does it as a thread that runs on the region servers. So essentially, it's a compute that is running alongside the data that is sitting there. And traditionally, if I have to look at it, you can look at them as database triggers. If I have to put it very simply, but it's not. You can write custom logic and push it in to your region servers and all that. But the problem is, there is a very, very fundamental problem here. The thing is, coprocess is actually an afterthought. They didn't think about coprocessors when they designed HBase or they designed Bigtable. They didn't think about locating compute along with the data. They didn't think about how they would manage new versions of the code to run along with the data. They didn't think about how failures will be handled if multiple such coprocessors are going to run on the same data store. So none of those were thought through because that was not the primary motivation of that implementation or that project, right? So for us, compute and data co-location is primarily, I mean, it's very, very essential, and coprocessors, we realize, is an afterthought. There are a bunch of issues that I spoke about, right? We have business logic upgrade, which is painful, service management, and the data store upgrades are painful. Failure semantics are not clear, noisy neighbors. So one coprocessor that you write might end up consuming a lot of resources, which might even inadvertently take away some of your cycles from the region servers or from other coprocessors. So these things are completely undefined, right? So that's not a good place to be. So the bottom line that we realized is that the applications need to own scaling. If I'm an application developer, if I'm building a system, I need to be responsible for the scaling end to end. What that means is that right from the request handling all the way to the way the data is stored, I need to have full control over it. If I need to own scale, I need to control scale, right? So this is the premise which we kind of, at least this is one of the learnings that we understood as part of this entire exercise, and then we realized that, okay, we need to own scaling, so what do we do? And like I mentioned, we kind of, just to summarize whatever learnings that I put down, right? If you want to build something in-house versus something that you want to use off the shelf, there are primarily few things that you look at. You look at the feature matrix, you look at how operable it is or how many moving parts are there. You look at if you have experts who can own the system that you're going to bring in, or you have experts who can build the system, something that you want, right? And are you in a position to take up that upfront cost, which is going to be like a few months or a years, depending on what kind of system you build, versus something that you're going to bring in off the shelf, right? So these are considerations that we had, and then we kind of decided that for a bunch of reasons, I think primarily because of the fact that our features were not, we didn't need a rich set of features that these projects were advertising. At the same time, we wanted more control over what we wanted to do, right? So given this orthogonality in the requirements that we had and in what was being, what we got, we said that let's just go ahead and build something and then see what it takes and productionize it. So thus, we kind of ended up building something which Ashwanth is going to talk about.
Hello. Hi, everyone. My name is Ashwanth. I'm a principal engineer at Indix. I know we have just finished lunch, so I'll probably be very light on you and also on me. So basically, so far, the context is we had these bunch of problems, and that forced us to that rendered us unable to use any of the open source solutions which we would have loved to use, but we had to build something on our own. And when you start talking about distributed systems, right, we talked about in the morning, Sriram talked about a lot of different consensus algorithms, and then we had another talk that talked about a lot of different problems that you face in a streaming solution, all of that. And when we talk about all these things, there are fundamental primitives that generally we assume or take for granted when you deal with distributed systems. And these are some of them. First is communication, right? We say they talk to each other. It's very easy to just put two boxes and say they are talking to each other, but there are quite a bit of problems that are there behind the scenes that you need to handle. Like the example is one is talking in Tamil and one is talking in Hindi, basically two different protocols which don't sync with each other. You basically can't communicate properly if one doesn't understand the other, right? So that's the first problem. And the next is the true promise of a distributed system, like sharding, scale infinitely, elasticity, all these different buzzwords that comes from different industries. So the fact that you should be able to have a reliable way to distribute your data, have them in smaller pieces, but have them at multiple places. That's the whole premise, because we know we can't vertically keep scaling up all the time because, of course, the disk is cheap, but it's not infinite. Your RAM is also getting cheaper. It's still not infinite. At some point, you will break a resource. Your machine will run out of resources. So you need to shard your data. And another one is routing. So once you have certain pieces of data available at different places, how does your system know where to actually go talk to, right? That's where the whole promise of routing comes into the picture. And next you have, my data is sharded, now I have more nodes into the picture, and the chances of my nodes going down because either of a process crash or a node going down, or in cases if you're on those unfortunate folks on AWS like us, where they choose to randomly kill containers or their virtual instances or reboot their physical machines at a whim, and say that's the promise, you don't get anything, it's elastic, keep changing it, right? But that's truly, while that's the promise, we don't generally work or build systems like that. So in order to circumvent all these practical issues, you need replication in place. But in reality, most of the times you are better off running things on a single machine, holding it in memory. But for all these weird cases, like AWS choosing to terminate their or restart their physical host, you need replication in place. And then finally, when you talk about distributed systems, you need to know that we are of the same team, right? If you and me, one of the examples where if one guy is a traitor, in the morning we had a talk, right? They talked about the general's problem. I need to reliably know this guy is on my same team. Like he's not somebody from another or circle who's not supposed to be replicating data with me. So you need a notion of a cluster membership. So these are some of the primitives which we realized that you needed in place if you're going to start building or thinking about distributed systems. So, and when we started doing it, there are quite I think 2 different teams at our organization started building same thing on their own way for completely different reasons. And then we wanted to combine those 2 together. And hence, this project Suchi was born. So it's open source and it's available on GitHub. So the name Suchi is a Sanskrit word which talks about index, which means index. The reason why I came up with that name, so the reason I came up with that name is one of the problems that I had to solve was storing data in an index with some sort of computes that I have to run along with them whenever I add data to it. So that's how it started. Essentially, it's a toolkit that gives you all these different primitives, and you can build any sort of business use cases that you want on top of this, or That's the promised idea. So what Suchi offers you out of the box is basically a way for communication to happen between different nodes. It sort of helps you route queries to the appropriate members in the nodes if you wanted to, basically access data at all once you put them back. And you need a way to detect your cluster members, so it sort of helps you know who is part of your cluster, who is not. And it also has ways where it can replicate data for you behind the scenes if you want to. And then you can have state, a local state, like for example, via an embedded key value store along with every node. That's how you truly co-locate data and compute. And again, the whole data part is optional. When we talk about, first time when you think about this, right, when I first time heard the same talk when we were rehearsing, it sort of occurred to us, right, if not all projects or all systems need a local state. In the traditional sense we think about it, right? So when we talk about, when we talk about state, we generally think of some kind of a database where I keep doing inserts or updates and doing selects. But sometimes when you work on problems, especially in say machine learning domains, you have the data, but the data is sort of immutable. That is, you have your machine learning models that you have to that's sort of your data that's co-located. And then you have to have computes scaling across different things, right? Those kind of data also generally could mean state for you. Most of the times, states are mutable, which means you have to keep updating them. In some cases, the state is just needed for you to run for your compute. Mission translations or any kind of classification. Machine learning models fall under those categories. And sort of Suchi gives you an abstraction where you can plug in any other key value store, any key value store you want for your operations to work. So let's go over one by one. The first thing is communication. So it sort of implements communication on top of gRPC. How many of you have heard of gRPC? Awesome. So for others who haven't, so gRPC is an RPC framework developed at Google. But G does not stand for Google. Do you know that? So every release, they keep changing the name of what G stands for. It's pretty weird, Google and their engineers and their standards. So we sort of implement our communications on top of gRPC. So gRPC internally uses HTTP2 as a protocol for communication. And they give you an RPC kind of layer on top where you can define your messages, you can define your services, and how they interact and all of that. And the other cool thing about gRPC, it supports streaming. Unlike in a traditional HTTP 1 or 1.1, you don't have a notion of streaming, whereas HTTP 2 has native streaming support in their protocol, and gRPC supports them. So as part of this, we provide two primitives for communication. One is called as the handle or forward. What essentially this means is it's a function that resides on your node that listens to a socket for any message. Whenever a message arrives, this code would get executed to check, should I handle this message? If not, whom should I forward this message to? It's as simple as that. And it takes these decisions based on the routing strategy that you plug it in, which we'll talk about later. And the other kind of communication primitive that this guy comes with is the scatter gather. Now, this is useful if you want to do any kind of aggregates on top of your data. For example, let's say I have these different, we use this for one of our stats collection framework where we distribute our stats across different machines, sharded across different machines. So whenever somebody asks for any query, like give me how much URLs have you crawled in the last day or something like that. So this guy scatters that request to all the nodes, like a broadcast, and each of them performs a reduction with their data, because my data and compute are co-located, right? So I can perform local reductions on each of those nodes. And the reduced data sort of comes back to the node that got the request. And from that, he does another reduction on top of this to give you the final computed value, and then give that back as a response. So to have these kind of operations or these kind of communications in your system, you would use the scatter gatherer primitive for communication. And the next thing is basically sharding or routing, right? One of the implementations we give out of the box in the library is the CH ring. So how many of you have heard of consistent hash ring? Okay, so people who have used Cassandra or read about Dynamo paper, you would be familiar with this. I mean, it's pretty interesting that this CH ring was published as a paper, I think if I'm not wrong, 1997, as a load balancing strategy. Instead of the typical round robin or least connection, somebody from MIT actually came up with an algorithm where you can effectively share the load across different web servers. And it so happens that the same thing can be used for your sharding and routing really goes together, right? So you can use that for that purpose as well. The main property being the amount of data that needs to be moved across in case of a failure. I'll show you an example. Let's say in this case, for some reason, node 1 went rogue, or probably it crashed or something happened. So what generally happens in the CH ring is each of those nodes, okay, so I should first talk about these dots. So this whole circle represents a full range of values of a function, okay? When you talk about a function, you take an MD5 as a function. So we know the output of MD5 is an 128-bit value, okay? It's like 128 bits. So your range starts from 128 zeros to 128 ones by flipping every bit for every number, right? So that's basically how you get the entire range of MD5. So if you put that entire range in a circle, where each point in the circle represents the MD5 range, nodes, when they become a part of the cluster, they decide each of the nodes would occupy n partitions for them. And they randomly take a value. Basically the approach we use is we take the host name and the partition number and compute an MD5 hash of the two. And then the output that you get would arbitrarily fall under somewhere in the ring, right? And you do that for all the nodes in the cluster, and that's how you get all these dots. Now, and each of the dots represent a particular key range between the two. So far, so good? Okay, so each of these dots, two dots, the circle or the chord between the two dots represent the, oh no, it's not chord, it's called an arc, yes. The arc between the two dots sort of represent the key range that the particular node can handle. So what happens is when one of the node goes down, the key that is, the range that is responsible for that node, that node was responsible for, gets shifted to its neighboring node. So this particular key range that you have here gets shifted to green, which is the node 2. This gets shifted to the node 4, and that gets shifted to the node 3. So it sort of randomly moves around the circle. And after that, the cluster sort of becomes like this when one of the node goes down. So the net result is, instead of trying to re-shard and re-replicate the entire data that you have on that particular node, you only move certain portions of the key ranges that are there to across your cluster. So that's basically how a consistent hash ring or a CH ring works. Okay, so the next thing is one of the important things in distributed systems, the membership, where the whole notion of consensus and other complicated problems come in, right? So we have two types of membership. One is a very shameless plug. It's a static membership. You basically have a configuration file, like how you have in Zookeeper, that says these are all the nodes that I have in the cluster, and you're done, right? There is no problem of consensus or anything. As long as your provisioning system is intact, your consensus on what are all the nodes in your cluster are intact, right? A very simple way to solve these problems. People don't talk about this, right? They talk about all these complicated algorithms, but it's much simpler to solve them if you think about it. No offense, Sriram, so don't take it. So the other type of membership is your dynamic membership. That is basically all these modern key value stores offer you, right? You can scale up the cluster, add nodes at whim, nodes can go down at whim, all those marketing terms. And this is where we have a beta implementation. We haven't fully tested it out. There are still some rough edges. We use an implementation called Atomics. It's a library that runs on JVM. So they implement Raft, which is one of the best implementations we can find for Raft on JVM. They even have Jepsen tests as part of their CI, where they verify that everything works properly and all of that. So we have integrated that for having dynamic membership within the cluster. Yeah, so the next thing is around the replication. So replication, again, is of two forms, the sync and the async. So the synchronous replication is like whenever you do a write, your write succeeds only if all the replicas have the writes completed. Else your write is basically blocked. The server wouldn't respond back with a message saying that it has completed the write. And the async is, yeah, I mean, so if you guys have been here since the morning, you probably have heard this async enough number of times in your life than what you have heard before. And that talks about how you can just consume writes and then eventually, replicate the data to other ones. Other nodes in the cluster. Actually, I think I overheard one of the conversations during lunch where somebody was talking there is no such thing as eventual consistency. It's just that you have a strongly consistent system, but it's just a little delayed. Probably somebody just missed a train or something. I don't know whom I heard it was during the lunch. So that's a very nice way to put it. So this sort of, the business or the industrial term is eventual consistency. They have these CP systems, AP systems, and all these different forms, right? So most of the AP systems which are highly available on partition tolerance gives you an eventual consistency kind of a model because it will take some time for the nodes to converge. So we have the synchronous replication implemented, but we don't have the async implemented yet because honestly speaking, we didn't have a need to on most of the cases that we were using. But again, it's open source. If somebody is willing to collaborate or if you guys want to give that a shot, you can also, we're more than happy to accept PRs or collaborate on all these things. The next one, the fun part is basically the storage. So we have a key value kind of an abstraction. And then we have a RocksDB implementation for the key value. So RocksDB, for folks who have not heard, it's actually a library, okay? Unlike when we talk about key value stores, we generally think about a system, right, that needs an installation, that needs setup and all of that. RocksDB is a library. It's actually written in C++, but they have enough bindings for different languages, including Java. So all you had to do is probably add a dependency in your POM or in your SBT, and it automatically you have the RocksDB available for use in your in your environment. And personally, we have had a lot of good experience working with RocksDB because there was another team who was using RocksDB for a different purpose. Basically the indexing team was responsible for using RocksDB for storing the data and then just giving it back via the APIs. And then we realized that's something we have good experience with. We understand how it internally works. So it's fair that we use that for all other things as we seem fit. So we added an out-of-the-box support for key-value abstraction on top of RocksDB. Yeah, so Suchi at Indix, we've been using it for quite a bit of systems. The first one was the HTML archive, which is what motivated us to build this in the first place. So it was a write-heavy system that used to take around thousands of transactions per second or requests per second for all the writes. And it used to store on 120 terabytes of URL plus timestamp indexed HTML pages that people were using for any debug analysis, or whenever your parsers are down, you need to have the copy of the page to go debug what went wrong during that time. The funniest part, or my biggest learning here is, this is the project that sort of motivated us to build all these things, okay? On any given day, no sane person would start doing or building something like Suchi for fun or for profit, seriously, right? And on any given day. We started it for doing that. And then once we got it implemented and working, at the end of the month, we saw our AWS bill. And then the first thing the management did was shut down the project. Because we were using D2. I think 2x large machines, which are very disk-heavy machines. And it became too costly for it to be used effectively to serve the purpose that it was actually serving. So, if you don't know, each of those machines cost, I think, around $2 per hour. You do the math, 2 into 10, that's $20 an hour, and then you have 24 hours a day, and then for doing for 30 days. And the amount of traffic we got for this system was also very less. So it was very hard to sell this to the folks in the organization to make it sustained for long. That's the truth. But yeah, it works. So the next thing that we implemented this is for the stats aggregation system. So we implemented all our stats as monoids. How many of you guys have heard of monoids? Okay, so it's basically a function that has an identity, and it is commutative and associative. So basically, I mean, you guys understand commutative and associative, right? So people teach us with addition at school for that. So but if you can represent a function that can satisfy this property, that is, if I take two values, a and b, and apply this function as a operation b or b operation a, or if I have three tuples a, b, c, and if I do a operation b and the result of that operation c, or a operation the result of b operation c, which is, okay, forget operation, a plus b equals b plus a, that's basically our associative. A plus, that's associative, right? Oh, is it? Oh yeah, correct. They can be changed, right? That's commutative, correct. So associative is how they're getting associated. Oh, that's how I remember. So a plus b plus c equals a plus b plus c, right? So that's basically how you join or associate these operations. If a function can satisfy both of them, and it has an identity property, that is, if you have just one element and you have an identity element for that function, for sum it's 0, for multiplication or division it's generally 1, right? The identity element. So that's generally what a monoid is. So we have our stat system built as monoids running on this Suchi, so that to distribute all these stats and have these aggregations running on top of the data that it has locally. And it sort of gives us the timeline and windowed queries. And it's for that we have the scatter and gather primitive that helps you scatter these requests to all these nodes and then gather the requests back and reapply the monoids on top of the result of the different, result of the results we get from different nodes to arrive at the final value. And the other thing that we were supposed to use this for, which we got the spike run but it never hit production at all, was basically a real-time scheduler for our crawler. So we have around, I think, 3 to 4 billion URL corpus that we have identified in the last few months. We keep deleting that often because our HBase cluster where we actually store them keeps going down every now and then. I think it goes on a vacation every 6 months, so all the data gets lost. And it's too costly to back it up on S3. So we just leave it there, and then we said, you know what, screw it, let's run all the seeders again and discover the URLs. And within a span of 2-3 months, we discovered that whole 3 billion corpus again. So that's basically how that system works. So we were trying to see if we can replace those. Today we run MapReduce jobs for more than a day to find URLs that I need to crawl for a day. Do the math, right? My job takes 36 hours to run to find URLs that I need to crawl in the next 24 hours. So by the time this job, you try to put them in a sequence, the time, eventually my crawler system is idle most of the time because I don't have URLs to crawl because the job just won't complete in time for me. Because it used to take like 15, 16 different signals from all these downstream systems. We can't scale up the cluster because it's too costly on AWS. You might have noticed that I keep talking a lot about AWS cost because that's one of the practical problems if you are in a startup where you don't want to give all your funding money to AWS. Instead, you would want to invest probably on the people or on some kind of innovation that you want to do because that's what is going to get you more money, and AWS is only there to grab more money from you, not give you back, right? So to solve those, circumvent these problems, we spiked on building a real-time scheduler that can, like some magic wand can give you just, okay, this is the next 20 URLs that you need to crawl for every batch that the crawler asks for. That internally was using Suchi to identify how do I distribute the data of all these different corpus and the algorithms that, the function that it needs to run, taking in so many other feedback of all these downstream systems and the previous past crawl histories that I have to arrive at should I crawl this URL or not. So that particular system was also, again, spiked, built for Suchi. It worked, but it never saw the light of the day because I moved and then Sriram also moved from that team to a different team. Practical problems. Nobody talks about this in distributed systems. Okay, so yeah. The thing is, the idea behind Suchi, right, having these pluggable components for different things is not new. to be honest. At least, I mean, this is a timeline that we have personally witnessed. So there is this library called Gizzard from Twitter. I think it got released in 2011. In 2013, they decided to archive the project for reasons unknown. When we asked in the issues, they said they have an internal fork of the same project which has diverged so much, and they think it's not practical for them to merge their open source version or the tree with their internal source, so they just decided to archive it. It's sad because it was a very good project, but and it was written in Scala, so it runs on JVM. Oh, I should have told, we are a huge JVM shop, so one of the things that we do is use a lot of Scala in our code, preferably any sort of JVM, because we trust JVM more than the ability for us to write any other language ka code, because when it runs on the machine, it might not be as fast as it runs to be. So the next thing was actually Ringpop from Uber. So Uber actually does a lot of really cool open source stuff, and one of the projects is called Ringpop. It's, I think, available on their GitHub. The problem was Ringpop was first written in Node.js, and then they later re-implemented the same thing on Golang. They still didn't have a Java version. So they promised, they said they'll have a Java, but unlike any other Uber driver who calls and cancels your requests, they also probably just deferred it for infinitely, where it was too unpractical for us to depend on them. So we started off building Suchi and got a first prototype out, I think, in a month or so, which was usable. That was around mid-2016. And late 2016, I think it was in October or November, in one of Okay, so in one of the conferences, the Google released a paper called. It's working. Oh, okay. Okay, so sorry about that. So Google released a paper called Slicer. Excuse me, Google released a paper called Slicer that provides a very similar kind of abstractions for their internal systems. They gave examples around their voice recognition system, their translation system. All those systems sort of used the Slicer, which is backed by their Chubby service, to have different layers on for service discovery, which is a kind of membership. And how do I route requests between them using their load balancer, which they call Google Load Balancer, and all of that. So they also published a paper that talked about something very similar. So that's what we sort of had to cover so far in our slides. So yeah, thank you. So any questions? Comments, feedback? Yeah.
So I was sort of looking at the code, Suchi code, while you're talking.
Oh, that's fast. Okay.
Yeah. One of the things that I noticed is that in your membership, you don't have any versioning. So for example, if you get a notification saying a new member has joined, different nodes get notifications at different time. Okay? So there is when a member joins, there's a part of the cluster that is aware of that member, there's a part of the cluster that is not aware of that member. And that can, in an update-heavy system, that can lead to confusion. So it would be, I think, better if you have a view membership. This is basically what the view stamped replication paper talks about, where you have a version of the cluster saying this is a new version of the cluster that has joined. And so everybody can quote that. So if you see other membership services that have been built on consensus protocols, they will actually reuse the underlying term number from Raft, because that is unique, as the version, saying this is the cluster based on Raft number, whatever. Okay. Right? So sure. Just the notification saying this is the version and this is the new member.
Sure. Yeah, that's useful insight. We'll take that as a feedback. Sure.
So, what other primitives have you added? So you have aggregate services. You've done membership and things like that. But are there any particular distributed systems primitives that you have added on top of this? In the sense, not primitives as in you have interfaces. For example, for storage, you have you have an interface to key value store. So you presumably have a get put kind of thing. But are you thinking in terms of, say, a immutable interface, again, a versioned interface, or a multi-version concurrency, a multi-version interface, where you don't just say overwrite, you say I update, but I can always get back something from an earlier version. Do you have had a need for it?
So far, we have not had a need for it because most of the cases for a given key, our values have always been like just blindly replace it. It's like basically, I mean, when you have these different events and you want to, when you have multiple versions, the strategy that you use to pick up the latest version is by timestamp, right? One of the things that that React offered out of the box and that had huge problems with the thing. So that's basically how it's been our use cases so far. So that's the reason why we don't expose the get as a multi-valued interface out so far. But yeah, I mean, if there is a need for it, if somebody else also wants it, we are more than happy to incorporate it and have the version detecting also as a pluggable strategy. You want something to add?
Any more questions for our speakers?
Just wanted some insight about the implementation of your replication layer. Mm-hmm. And when you say that it's all sync today, in the case of a multi-node setup, I mean, having just sync replication to all nodes doesn't seem like a very practical strategy. I
mean, the thing is, we could re-implement the whole Cassandra in this system, right? For example, you can have, one of the things we wanted to do for our hackathons, that kind of thing, was like for the anti-entropy using Merkle trees, where you can sync which are the keys that are missing and then eventually sync them back. But we realized that approach A was complex. I mean, you had to write the code, maintain it. The second thing is, on the more practical approach to doing it is just terminate the box, restore it from the last backup or backup from one of those machines, and then replay the data. It was much faster, and it quickly came onto the sync where we want, rather than to say my system will like automatically handle replication internally. That's one of the reasons why we kept the replication also as very simple. Again, the context is we didn't have a need for building something like that. And restoring from backup and replaying the old events sort of fit the bill, because there was always other replicas in place which would can always handle those things. So that's the reason for going with it. Sorry?
Yeah. The other important aspect is also the operability part. I mean, it's, even if you look at HBase reassignment or Cassandra reassignment, right, you're kind of left in this state where you don't know when it's reassigning, when it's complete really. Sometimes you end up in this limbo state where the Zookeeper and region servers keep talking about this region not closed, it's not available and things like that. So sometimes you end up in these situations where you're not able to understand what exactly is happening. Instead, if you had a little bit more predictable, but like a simple automated approach where you can just recover quickly, right? That is something that, we felt that ease of operations was something that is a prime factor for us to decide whether a feature should be in or not. And to put it even more open, right? I think it's also about whether we have real use cases for it. Do we have really like these kind of systems that we want to keep running and operation? We don't have that. So it's as simple as that. Again, it's open source. We put it as open source right from day one because we wanted to see if there is anything else that people are interested in, and we can kind of incorporate that. So pull requests are welcome.
The kind of systems you can build when you know a lot of things, or when you can take a lot of things for granted, especially when it runs within your infrastructure or your network. It eases off a lot of things.
Yeah, so I had a question. So suppose I implement, so I didn't understand it actually. Suppose I implement my deep learning model in, say, Java or anything without using any framework, and that I have got a dropout option in which in every run, I have a different probability of getting, so in every epoch, I have got a different neural network, basically. So do I submit my code to Suchi, or do I use Suchi to build a distributed system so that my code works? I didn't understand that.
You use Suchi to build it. It's not a live service that's running that you submit something to it. It is not like that. It is a library. You take that library, see what features are coming out of it. We kind of went through a bunch of features that is coming out of it. We could use that to actually build something. right? So you could, if you wanted to say that, okay, if you wanted to really build like a distributed deep learning training infrastructure, you could do something like that with Suchi, where you have, I mean, basically one of your nodes will be the parameter server, and a bunch of other nodes are actual worker nodes, which is doing the baproc on each of those nodes, and you push your updates back to the parameter server does the updates and sends it back to all the guys, and then it does internal operations, right? So you could do this, but Suchi is not offering anything out of the box. You need to do stuff on top of it. It provides the low-level primitives or the low-level interfaces for it, right?
Use Suchi for is to learn how some of these distributed systems actually work, right? I mean, that was one of the other motivations for at least personally me to start this project in the first place. So if I wanted, I mean, one of the things that we want to do is, okay, we talk about Cassandra, right? You read a lot of documentation that says this is how it works. They have the data stacks guys have these pretty pictures on how these replication works and all of that. But there's nothing like you trying to look into the code and understanding how it does. But if you're new to any code base, any foreign code base, it's going to take a while for you to understand how the whole flows built and structured. And one of the approaches, again, personally, I find it useful is, can I start implementing the same thing and just to get a feel of how it actually works? Or can I start implementing the same thing to appreciate the complexities that are there in building a system like that? So this Suchi is also like a ground for us to experiment and try new things, understand how it actually works, and see if it's something that can be useful to push it out to others, or probably, you know what, it's yeah, just a vague idea, like one of those other daydreams you have. Yeah, so that's it.
Any more questions? Anybody?
Cool. Thank you, folks.